Hello everyone, my name is Sergey and this is Milena and Marto.
Hey!
And we are here to present you the case from the dataton, which academia dataton, which Sergey mentioned. The case was related with the cryptocurrencies, the hot topic nowadays, and the problem was, the problem of the case was to make basically financial time series prediction, and the case was separated in two levels. So first level was to make the prediction, which will be the focus of our presentation today, and the second level was to automate it, so to make sort of AI or trading model. So the data which we were provided was a data of 5 minutes steps period for 24 hours of many cryptocurrencies. I think it was about 1,000 cryptocurrencies. And the period, it was 2.5 months, so it was like 15,000 observations. And the task was then to make a prediction of 20 major cryptocurrencies, Bitcoin and so on. Yeah, so basically this was the task, and before my colleagues continue, there was one special thing, that the prediction should have been made one step further. So if it was a 5 minutes period, the prediction should be made one step further, then compare with the actual, and then take all the previous periods and then make one prediction further. Okay, so I leave the word to Marto. He will continue how we proceeded further.
I'm mainly going to talk about data preparation. Initially, we noticed that the data has a very large gap in it, and we decided to use everything after that gap because it was more consistent. What you see is the trends of actually the volumes of the 20 cryptocurrencies which we were supposed to forecast. Besides figuring out how to fill the gaps, we decided to merge the separate data files into one data frame. We added 3 columns which we thought would help us for modeling, but we never ended up using them. They are nice to give an indication of where exactly we're missing data. So that's essentially what we did initially. By examining the trends of the prices of each cryptocurrency, we noticed that they pretty much follow the same pattern. So we assume that if we focus on modeling just a single cryptocurrency, the models and the methodology will apply to all other cryptocurrencies as well. We decided to focus on Bitcoin, and what you see here is actually the price of Bitcoin for a given time period. One of the first things we did in our experiments is figuring out if we can make it stationary, if we can make this process stationary in a simple way. And log returns seem to have been a very easy solution to the problem of non-stationarity. We also did seasonal decomposition. There's a function in the stats models package of Python that does this very easily. And that once we did the decomposition, we noticed that there really isn't a strong seasonal pattern. You'll notice that it ranges from -30 to 40, which is not really that much of a span compared to the ranges in which the actual price fluctuates. The residuals were also not that significant in terms of their span, so we determined that the primary component of this time series was the trend itself. You'll notice that this pretty much looks like the original time series. The only major difference is that it's smoother. And looking at it, there really isn't any obvious pattern. There isn't a trivial mathematical formula which you can use to describe this kind of a trend and hopefully predict many times takes ahead using that. The way it behaves is it keeps moving in a single direction for a while, and then it suddenly changes direction due to who knows what. I mean, someone says something in the news, complex social economic factors which we can't model in a day, which is all we have. So we decided to do autocorrelation analysis on this trend to see if there isn't any dependence between the variables, between the values of the variable in time. And what you see in the upper left corner is the autocorrelation function. And at first glance, there are lots of points outside the confidence interval. So this could lead someone to assume that there is very high autocorrelation in this time series, meaning that the current value of the price is strongly dependent on many other values that came before it. But if you look at the partial autocorrelation functions, which are at the bottom, they tell a different story, and it's one that we should believe. They basically tell us that there is no strong autocorrelation in this time series. There are maybe only like 3 or 4 points outside the blue zone. So if we are going to model this time series with an autoregressive model, we shouldn't use models that exceed order 4 or 5. That's like the maximum we should use. So low order models should be used for in this case. And I'll talk briefly about 2 of the models that we tried out initially. So one of them was an ARIMA model. R actually has an ARIMA auto-ARIMA function which basically determines the order of the model automatically. And it came to the conclusion that order 111 is the best model to use. So autoregressive first order differencing to get rid of the non-stationarity, and first order moving average. That's the model that was automatically computed by the function. And it seems to work pretty well. It did better than the baseline model, and the baseline model was essentially just using the previous value of the price to predict the next value. It's like the absolute most basic logic you can use. And this auto-ARIMA model managed to outperform it a bit. The reason we didn't rely on it completely is because our implementation was really slow. Perhaps we didn't implement it properly, or I don't know what. But we also looked into other alternatives. One of our teammates who isn't actually here, he tries to train a neural network to predict the future price of the cryptocurrency. I believe he used an LSTM network, and it didn't really give good results. In fact, it was rather poor. But that's to be expected. As you saw from the autocorrelation analysis, there really isn't any long-term pattern in this time series. The current value depends at most on the previous 3 or 5. There's no point in looking for long-term patterns in Bitcoin prices because there don't appear to be any. So I think that's why the neural network didn't work in this particular case. And Next up is the other model which we developed. And I'll hand over to Morena to explain about
Thank you. As Max said, our best performance model is Autoregression. In the beginning, we started with lots of regression models, but in the end, we decided to use linear regression with high geometrics. What is high geometrics? Is this one. It is a matrix which is a single matrix with diagonal left, right, which is a constant, as you can see there. Our linear regression works like Autoregression because of the Hegel matrix, because it uses each row of the matrix uses the value from the previous row. We started our model with this flat, but because of the plot that flat shows, we expected that not all of the coefficients will be statistically significant enough, and we wanted to create an optimal model for each cryptocurrency. We didn't want to use one model for all of them, and what we had to do, we should optimize our algorithm to create 20 different optimal models. As I said, we used 6 coefficients in the beginning, and not all of them are good. For example, when the algorithm creates the first model, it uses all of them, but the p-value of history is bigger, for example, 0.05, and it's not statistically significant enough, and the algorithm removes the sum automatically. Then the process starts again, and the algorithm creates a new model with the rest of the coefficients. If we have, for example, 5 or 4 with p-value bigger than 0.05, the algorithm compares them and removes the bigger one. And for example, we have only 1, 5, it automatically removes again, and we have a new iteration with a new model for this cryptocurrency. And in the last case, we have only 4 coefficients which are statistically significant. This step is repeated multiple times until we have all the coefficients for all the cryptocurrencies with p-values under 0.05. And these are the models of the length cryptocurrencies. We think it could be more things, so we zone the chart so see only the first 20 time period, and it's not the whole chart. You can see probably the black line is the real price, and the red line is our prediction. They're not the same. You can see here, for example. So we can say our models are not overfitted. They perform very well. So we almost win. And now Sergey will explain some of the matrices we calculated.
So each model should be evaluated, and we used several metrics. Don't be scared of the formulas. Just to show which metrics we used to evaluate. So we used just square to measure the goodness of fit of the model, the mean absolute percentage error, to measure the model accuracy, the prediction accuracy, the directional symmetry. As absolute percentage error does not measure the direction of the prediction, this coefficient shows if it's same direction as the actual value. It shows 1 plus 0, and this one is coefficient of variation. It's basically coefficient of variation of this metric, but we use it to evaluate how a model behaves in different scenarios, in different days, and for different cryptocurrencies. Yes, for adjusted R-squared, we use color scaling. So these are the 20 cryptocurrencies, starting from Bitcoin, Ethereum, etc. And here are the 5 days which were given us to evaluate the model. So it was made by the organizers. Yeah, so and here the color scaling shows the minimum being the worst and closest to 100%. So the widest being the best adjusted R-squared. So you can see that we obtained quite a good result in terms of this coefficient. And in some days where the model didn't perform that well, with the average 91.2%. For the second coefficient, also here is the darkest being the best, and the maximum, the lightest value being the worst. We obtained average of 0.70%. So here you can see the best result. Here you see the worst result. And in order to understand is it so good or not so good, we decided to compare this coefficient with the base model, meaning if we take the previous result and just put it forward, what will be, so like 1. What will be the result, and the result will be 0.34. So this way we could compare if the model performs well, and it performs quite well. And this one was the coefficient of variation. So we see that in this day the variation, the model performs with the maximum, with the minimum variation, and here it performs better. And the last one, directional symmetry. Here also, the closest to 100 is the best, and here is the worst. So we also use this color scaling to see where model performs better, and we obtained the average of 63.05%. Yeah, so basically that's it, and thank you very much for your attention. Invite you for questions.
Can you say a little bit about yourself? Because actually I'm not familiar with the data and so on. I have no idea who everybody is. Like just people say you're the winners, and that's fine, but
No,
you're
like we were in finals.
Yeah,
no, you're not even the winner.
No.
The winners are in another country. They just went to.
Can you just present yourself with 2 words?
Yes, so we are participants of the datathon. We represent one of the teams. So actually the organizers of the datathon, Data Science Society, they sit here, all the organizers, and specifically this datathon was academia datathon, meaning that it was between the universities of different countries, in Bulgaria and different countries. And we represented, I don't know if you know the university, but it's the University of National World Economy, so economics university in Bulgaria. Actually, master is from technical university.
Yeah, like the black sheep, I knew only one.
You are the best sheep in our team.
But we being from economics university, we appreciate it.
Yeah. Are you full-time student?
Sorry?
Are you full-time student?
Or
Are you teaching assistant? Or?
I'm doing my master's degree. Everyone is different.
Started a PhD, so.
Okay.
And
Thank you. Okay. So you said that there might be a pattern, but this pattern is hard to detect with LSTM just based on price. I'm interested if you have tried other models that also use other data, not just the price data. Let's say the blockchain data, probably account distribution histogram, probably some sentiment data. Have you tried this model?
I'm assuming it can be done, but we really didn't have a lot of time to do it. We have like 1 or 2 days to develop a solution. And actually, as I said, the guy that did the neural networks and who's really into neural networks, he isn't here right now, and he is not able to explain in more detail. So sorry.
Okay, thank you. Have you tested this solution with the different data sets? Same model, like to get another 2 months and see what was the prediction?
There was only one data set that just provided different days, like different slices from the data set to use for this.
But after that, have you tried just to see?
No, we haven't done any further data collection or further validation.
Right. So if that works, then you guys actually saw everything with real money.
You know the hard data because I'm not a gambler and I wouldn't do that.
I tried, but
It's available for research purposes. Yeah, the code isn't secret or anything. It's uploaded to the data science society platform. It's an article, so.
actually, everyone you can try with this data, so everyone can test and try and to try to beat them.
As long as
Just download the data and try it yourself.
Yeah, as long as register, of course, and being part of your our site, but we assume that you are because the registration for the event. So yeah. Okay, you can try, and this is what we are trying to do every time with these data sets. They're available for everyone to try test data sets, and yeah.
Could be applied similar steps here, building model for analysis. Is it's not only for cryptocurrency, but in similar way, or there should be a specific approach for specific domain knowledge. This exclusion of questions, I've seen it done in other places as well. So it could be possible. I actually do it in my work. It's possible to.
So all the data where data secret and you test it after fitting the model, or is it the data you fit the model? The performance.
That's something I tried to explain in the beginning. So the concept is that you take, for example, we took 6 periods, so that means 30 minutes, yeah. 6 minutes, 6 periods. Then we took it as a testing set, and then made one prediction further.
No, we have like
training
set.
Yeah, that's a training set. And then we took 7 periods, and then we made one prediction further. So the training set increased. So each time we took the training set as the previous period of time, and this solution is quite specific because the prediction is not made for 20 steps ahead. It's made only for 1 step ahead.
Only for the next step, step that the model cannot do.
Yes, exactly.
Have you tried on different time frames and using daily?
Yes, that's actually the last tables which I showed. There were 5 different days, and I think they were more the hardest to predict because the volatility was very high at those days, and they were selected from the whole period of time of different days.
probably he didn't get it. The data was, and the conditions was that they have to use the 5 minutes data, and this was firmly the condition. So they only used the 5 minutes data. This was in the rules.
Have you tried the model with 2017 data, 2016, because there's a lot of